Yeah, please, your 30 minutes starts now.
Okay, so good afternoon, everybody. I am Pornpavit Kapkert, and my thesis is Bioenergy Supply Chain Simulation and Improvement based on Thailand Alternative Energy Development Plan. And my advisor is Professor Elena Kriasina. So let's first start talking about the background and problem of my thesis. So in Thailand, we have our own energy development plan called Thailand Integrated Energy Blueprint. And this blueprint consists of 5 energy plans which describe different view, different goals, and different policy of energies. But I want us to see on this one, the AEDP, the Alternative Energy Development Plan. In the AEDP is determine the alternative energy consumption goals in several alternative energy. And if we see in this year, in 2021, some alternative energy, such as solar energy and wind energy, they already met the target as stated in AEDP. But for some alternative energy, as you see in the right table, for example, the electricity generated from small hydropower, from biomass, from biogas, from energy crops, solid waste, and also bioethanol, they haven't met the target yet. There are some kind of several megawatt that different from the target. And with this reason, I want to investigate that why Thailand some alternative energy type haven't met the goal. Why in some alternative energy such as wind power, solar power already met the target. So there are 3 objectives in my thesis. The first one is to simulate the current Thailand bioenergy supply chain. And in this thesis, I will consider only electricity generated from biomass, electricity generated from biogas, from energy crops, and bioethanol only. And the second objective is to investigate the problem that make the real bioenergy consumption less than the target, such as whether we lack of the biomass or we don't have enough facility to support the AEDP. And the third objective is to make some suggestions to help Thailand to accomplish the AEDP target. And here is some state of the art that many study about bioenergy supply chain optimization. And in the left side, this study about what the consideration issues that we should consider when doing the bioenergy supply chain optimization. The first issue is the logistic process or logistic activities occur in the supply chain. Biomass harvesting, pre-processing in the supply chain for biomass, the storaging, the transportation, and energy production. The second issue is the objective function. What the objective of the optimization? To minimize cost, to maximize profit, or maximize NPV. And the third one is the methodology we use to do optimization. Mathematical programming or use some simulation software. And in the right side, this is the bioenergy supply chain study conducted in Thailand. This study about the electricity generated from biomass in one province in Thailand. His method is the mixed integer linear programming. His objective is to minimize total supply chain cost, and the constraints he considered in this paper are the inventory constraint, biomass usage constraint, biomass power plant selection constraint, and supply and demand constraints. However, in these papers, they consider only one energy system, which is the electricity generated from biomass, and they study in just one province. But in my thesis, I want to study 3 different energy systems, which are the electricity generated from biomass. The second one is electricity generated from biogas from energy crops. And the third one is bioethanol production. And in my thesis, I consider the whole country, whole Thailand, not just in one province of Thailand. So this make my thesis different from the existing papers, existing studies. So first, let's see about what is the Thailand bioenergy supply chain workflow in my thesis, right? There are four players in the supply chain. The first one is the biomass suppliers who supply different type and different amount of biomass. Here I consider 77 province biomass suppliers, and in Thailand we have 77 province. That means I consider all province in Thailand, and I consider 17 types of biomass. And the second player is the transporter who transport the biomass from biomass supplier to power plants. The third player is the power plants uh, who who produce energy, right? In this thesis, I consider biomass power plants, biogas power plant, and bioethanol plants. And in Thailand, biomass power plants, we use three different energy conversion technologies, which are direct firing, or another name is direct combustion. The second technology is gasification, and the third one is cogeneration, or CHP. For biogas power plant in Thailand, we use anaerobic digestion process to produce biogas from biomass first, and then use this biogas as a fuel to feed in the boiler to produce energy. And for bioethanol plant, we use fermentation process to produce ethanol from molasses and cassava. Sorry, cassava. and and different different technologies have different energy efficiency, as you see in the red color here. And finally, the fourth player, the consumer, who consume energy from power plant. And here I consider the national consumption as stated in the AEDP. And I forgot to mention that in my thesis, I have totally 427 power plants. Uh-huh. In the optimization of my thesis, I divided into four scenarios: case 1, 2, 3, and 4. In case 1 and 2, I want to find out how much the bioenergy potential that Thailand has in the present. And in case 3 and 4, I want to answer that how we can improve the supply chain to help Thailand meet the AEDP target. So in case 1 is we find the current bioenergy potential of Thailand first. Then in case 2, I improve the supply chain from the case 1. In case 3, I want to answer that how much biomass Thailand should grow more or should have more, and how many and how much capacity of new power plants Thailand should build more as well, and where to locate those new power plants to satisfy the AEDP target. And in case 4, I improve the supply chain from case 3. In case 1 and 3, the objective function is to minimize total cost. And in case 2 and 4, the objective function is to minimize the maximum inventory level. I have totally about 7.5 million variables, which consists of the amount of biomass delivered from supplier to power plants, the amount of bioenergy fed into the energy production process at each time step, the inventory level of each power plant, maximum inventory level of each power plant, and in case 3, we introduce new variables, the additional biomass Thailand should grow more, should have more, and the plant selection. The parameters inputted into the model are the biomass available from supplier at each time step, the distance, the plant's profiles such as energy efficiency, maximum capacity, cost, so on and so forth. And the final one is the national demands. And the constants I consider are biomass available limitation at each time step and from each suppliers, the inventory limitation and inventory change, the power plant maximum energy production limitation, and the last one is the balancing between energy produced from power plants and the national demand. And I have to mention that I consider monthly time step. So in a year, we will have 12 time step. And in this, I use Python version 3.9 to do the mathematical programming. So let's see case 1 and case 2 result first. From the case 1 that we want to answer that how much bioenergy potential that Thailand has right now. So from the result in the case 1, we know that Thailand currently has bioenergy potential to produce electricity from biomass for 2,550 megawatt. Electricity from biogas from energy crops for 35 megawatt, and bioethanol for 4.79 million liters per day, which means the bioethanol can potentially satisfy the AEDP. But for electricity from biomass and biogas, these two haven't satisfied the AEDP yet. And the total cost of case 1 is about 375 around this billion THB. The THB is the Thai currency unit, which $1 equal to about 31 THB, and 1 THB equal to 2.3 rubles. Okay, and from case 1, the inventory utilization, the overall inventory utilization is about 41%. And the percentage of operating plants of case 1 in overall is about 75%. And in case 2, I changed the objective function from minimization in case 1 to minimize the maximum inventory level, as you see here, and see how the supply chain will improve. The total cost is about 500 billion THB. The overall inventory utilization is about 74, 73 around this percent, and the percentage of operating plants, the overall is 100%. And what is the benefits of having higher inventory utilization and higher percentage of operating plant? So let's see the inventory utilization first. The higher inventory utilization means that we have a lower inventory level, or in some cases there is no inventory level, no need to stock biomass in the inventory at all. And this means that it's easier when consider about the inventory management. It's easier to manage on this, and also that means there are less bottleneck occur in the inventory before we feed this biomass into the energy production process. And also there is the less possibility that the biomass will perish. And in terms of percentage of operating plant, the higher number of operating plant mean that the work or the labor are distributed in all over the country, all over power plants, not just congest in some plants. So in terms of socio-economics, it is better. But in my case, I didn't go deep into the socio-economics. And in case 3 and case 4, we want to answer that to meet the AEDP, how should Thailand do to satisfy the AEDP? So from case 3, that I want to answer that how much biomass that Thailand need more, and what the capacity of new power plant, and where to locate them. In case 3, the results show that Thailand need more or less for about 32.7 million tons, or sugarcane for 4.65 billion tons equivalently. And the capacity of new power plant, capacity of new biomass power plant is 3,100 megawatt, which locate in Sratburi province. As you see in the map, it is here in the central part of Thailand. And about 64 megawatt for biogas power plant, which also located here. And the total cost of case 3 is about 1,300 billion THB, while the inventory utilization is about 0.4, which is nearly zero, and the percentage of operating plants is about 91%. While in case 4, the new capacity biomass power plant is 1,600 megawatt, and new biogas power plant capacity is 51.8 megawatt, which also located in here, Sarapuri province. And the total cost of case 4 is about 8,000 billion THB, but the inventory utilization of case 4 is higher. It's 84%, about this 84%, and the percentage of operating plant is 100%. So in conclusion, in the present, Thailand has bioenergy potential to produce electricity from biomass at 2,550 megawatt, electricity from biogas from energy crops for 35.65 megawatt, and bioethanol for 4.79 million liters per day, which can potentially satisfy the AEDP target. And the additional biomass is the sugarcane for 4.65 billion tons, right? That Thailand need to grow more. And new power plants are located at Saraburi province in the central part of Thailand. New capacity of biomass power plant is 1,630 megawatt, and new capacity of biogas power plant is 51 megawatt. However, if we see in the diagram in the two previous slides, we can see the trade-off between facility utilization and the total cost, right? And my suggestion is Thailand should reduce the biogas from energy crops target and increase the electricity from biogas from solid waste or from manure instead, because solid waste and manure give about 5 times higher methane content than energy crops. And by doing this, I believe that the additional biomass here also be lower. So Thailand doesn't need to grow so much biomass here. And for the future works, we can include the transmission line network constraint. Since here in my thesis, I didn't consider the transmission line network constraint because I couldn't access to this data. And according to the AEDP, it stated that in the present, Thailand doesn't have enough the transmission line network, transmission line capacity to support all alternative energy production. So if we possibly consider the transmission line network, I think we will got more practical and more precise result. And another possible work is we can change the objective function. So from just minimize the total cost to maximize NPV or maximize profit, and then we can see how the supply chain, how the optimal result will show us. And for my contribution, I upload my thesis on ResearchGate and also Python codes and all datasets that I use to optimize in this thesis. I already upload them on GitHub. And finally, I would like to thank Professor Mongkol Itipalin and Professor Thanapon Cheranai who support additional information to me from Thailand, as well as my advisors, Professor Elena Kriasina, for helping me to finish the thesis. And this is all my presentation. Thank you for your attention. If you have any question, I'm ready to answer. Thank you.
Thank you. Dear committee members, it's time for the questions. Please, if you have any. Maybe then I will ask at least one question. You mentioned some mathematical programming approaches. That means that you use some, say, for example, linear programming technique or convex programming technique. Which one exactly did you use during your investigation?
Okay, so in what I present, I didn't show the mathematical programming, but I will show you. So maybe I show the case one, for example. Is this okay?
Yeah.
Okay, let me take a moment.
Oh,
Okay, so here, so this is the variables and
I see. Yeah.
parameters, and
Mhm.
let's start with how can I find the bioenergy maximum? Sorry, the
I see.
bioenergy potential. So first, I try to maximize the electricity from biomass, okay, which is DELC here, and electricity from biogas, which is GELC, and ethanol, DETH, right? And the constant is as following. And I got the result right from the possible energy potential that Thailand has, and then I use this result as the parameters. Yes, this is the answer, and I use that those things as a parameter to optimize in this uh, in these models. So the model is to minimize the total cost, which consists of biomass cost, the transportation cost, production cost, and holding cost. Each of them described on this one. Okay, here, and this constraint is the same as the previous one because we have to limit the biomass availability, so on and so forth. Yes, and the result, as I already told you. Is this answer your question?
Okay, and just a small question. Is it possible that the solution of your problem, of this problem, is not unique?
Not unique. Sorry, what do you mean?
That means there are a set of optimal solutions.
This one is linear, so I think it's
Yeah.
unique. Yeah. Hello.
It seems that again some poor connection of our chairman, so we'll wait for him to come back.
Meanwhile, maybe I can follow up the question of the chairman. Yeah, so the question was related, you may have more than one solution with the same objective function cost. Is it possible in your problem?
I think because my problem is linear programming, so I think it's just one possible answer to satisfy the objective function.
So linear programs cannot have multiple solutions.
Yes.
Actually, they can.
Okay. Maybe you can enlighten me here.
Let me ask you another question about, you have a model which actually requires a lot of data and mainly related with the future, right?
You mean?
For example, the demand. How is the projection of the demand?
Here in my thesis, I consider the national demand according to the plan AEDP. So it's, let me go back. Here is a target. So I balance this biomass to this number, biogas to this number, and ethanol to this number.
But let me ask you the question in a different way. So wouldn't your parameters of your problem in somehow become stochastic, that you have not full information, or they may change in the future?
Sure, yes.
Yes. So how you deal with that? Like if you must make a decision today, but some of your parameter will change, your optimization problem will give you some suboptimal decisions for the true parameters, because you still don't know. So how you can deal with this? Have you make any sensibility analysis, or how you can deal with this type of problem?
Yes, as what in my mind right now, we can make some kind of a stochastic condition on the demand parameters, right? And yes, if we have allowance on the chain just 5% and 10%, and we can optimize the result, and we see. This is what in my mind.
Okay, but you have not. I mean, like, you have not some quantification of that. How important is the uncertainty in your problem? Have you quantified?
No, the next is no, because I just fixed the target consumption.
Mm-hmm. Yes, I have no more questions. Thank you.
Thank you, Professor Pozo, for the support. Are there any other questions from the committee members? No. Then external reviewer also does not have questions. And in this case, now it's time for scientific advisor, Professor Grazina. Please.
Yeah, so the work presented, the topic of this thesis is a bit, well, not quite ordinary. It's not of the field of standard topics we deal with, but that goes from Pornpavit's interest. He was really interested in this alternative energy plan and incorporating alternative sources like green energy sources. Well, I would like to say that actually he didn't have enough, well, the timing was not perfect, and most of the results were baked like last moment. That's why, like, the original plan to provide a sort of useful tool with a proper user interface, this plan was not realized. But I think Pornpavit really made huge progress in understanding how to model like such a complicated supply chain, and well, I think his efforts really deserves to be like appreciated and graded. Yeah.
Okay, thank you. Thank you. Now I have to ask Pornpavit the following question. Are you satisfied with the defense procedure, or you have some comments or something like that?
Yes, I'm satisfied. I have no problem. Yeah, it's good.
Okay, then now it's time for your final word, please.
Okay, so thank you all committees, and for all questions I have today. It's really useful, and it is possible to think for the future work. And I would like to thank again my advisor, Professor Elena Grazina, who support me all along in this year and finally finished this thesis, and all my colleagues who support me. Yes, this is all. Thank you so much, everyone. Thank you.
Thank you. Now, dear